In this video, I'm going to show you how to derive the Vasicek stochastic differential equation as it is used for the rates model in the context of financial engineering. I'm going to derive the rate and then the expectation and the variance. I'm going to also show you how to price a zero coupon bond under the Vasicek model. To solve the equation, I'm going to use the toolkit provided by typical differential equations. Just here we will have a stochastic term. There are many other techniques to solve the Vasicek model. They all yield to the same result. The one that I'm going to use is somehow long, so this is going to be a long video. This gives us the movement of the rate. What we have here is the rate as well on a deterministic term, and here we have the variance and the diffusion as a Brownian motion. So the solution that we're looking for is gonna be something like this. When you solve a differential equation, you will have to isolate the rate and then have a function here of something without r. So this is what we're looking for. The typical technique to solve this kind of equations is to use an integrating factor. The integrating factor is gonna allow us to separate the term in R here and merge it with the terms in R here, so to arrive to a solution of the form like this. So the integrating factor technique tells us that if we have something moving like this, and here we have this other term will be linear and then a function. So what we want to know is the movement of y itself. We're going to get this term, and the integral, the exponential of the integral, will be the integrating factor that we're looking for. So basically, the technique of the integrating factor will allow us to use a trick like this. And then it's kind of the rule chain. This will be the total derivative of x times y will be a chain rule. So with the integrating factor, we're gonna arrive to something like this that will allow us to separate the r terms. So going back to our equation, what we have, separating the terms with r and the ones without r, is something on dt, and then the other terms that are not of our interest for the moment. So we're going to apply this integrating factor that will be the integral of the middle term on both sides, just to use the trick that will allow us to solve the differential equation. So I'll have the same on both sides, and then we leave this part as it is. We concentrate in this part here. So we can actually expand this to show a little bit more what we got. It's a term that it's on dr, the differential of r, and then this here that looks like if I have the differential of the exponential and then r dt. Here, this part, I just leave it as it is for now. So we can see here that we have in all this term kind of a chain rule that will be this without the derivation, the derivative of r, and then kind of if I have derivated this here and this without derivation. So this can be written as the backwards of the chain rule, as if I have done something like this. So here we just got rid of one of the r's, and then we have something that will allow us to get rid of one r term. And on this side, I'm gonna have something that doesn't depend on r. So now to get rid of this differential, the last part of solving by integrating factor is just applying the integral. Gonna use these integrating terms that it will be today the spot. I'm just gonna call S. You can start from T0 if you want. I'm just gonna start from TS. This is what all books usually use, and then the integration of this, and then here I'll have the same integral. Just gonna use this notation EKT, and everything that remains the same. So here I'm just missing this term. What we're gonna do now is we can expand this here and here linearly, and we can also expand this to try to get rid of the integral and get a pure term in R. So for now, to get rid of this integral here, just remember this part is the theorem of calculus, that if you have dr dx, for example, AB, you can't say that you've done this, which is this, and then this will be the solution. So we're gonna use this as well. So using the above to get rid of the integral, we will have something like this. It will be E evaluated on the first limit, and then we'll have the same evaluating on the second limit. And then here we can just expand the integral from A, K, T. Here we'll have the deterministic term, and then we'll have the other term. This can, the variance can go in and out because it wouldn't depend on the stochastic part. Then we'll have to pass this to the other side and solve for this actually. So the final equation will be the rate that at the time step that we're looking for is gonna just depend on some constants exponentially. This will be the rate at the starting point. This is like R on T0, so this is known. And here we'll just have some other constants which are deterministic terms, and then we'll have the stochastic terms. I'll leave it for now like this. This will be a solution just because we have the value of the rate at the time we want, and then something that doesn't depend on RT. Now what we can do is we can solve this part if you want, just to make it neater. So for those who want, we're gonna now work on this term AKT. You can work it out. This will help you on your simulations. You'll have to derive this. So what you can do is, first of all, leave all terms that you're not gonna need out, and just keep the terms who actually depend on dt. This is just simple as this. Okay, sigma. Okay, this goes out of kt on starting point, final point. This will lead to E minus k ds. This is usually the solution that you find on textbooks of the Vasicek equation that now can be written like this. Starting point, and then here you have the terms that are corresponded to the mean reversion, and then you'll have the other terms are part of the Brownian motion diffusion. Here, if you want, you can put WT. This is the Brownian motion that changes with T. Another way to write the Vasicek solution. Now, we know that this is deterministic. This is deterministic. This is just the summation of Brownian motion. So usually what you're asked to solve is for distribution of RT. Also, you'll need the distribution to know how you're gonna simulate it, and then we just know that RT distributes normal with some expectation and some variance, because this term is normal and this is just the summation of independent normals 0, 1. So we're gonna find the expectation and the variance of the rates under Vasicek model, because this will allow us to draw simulations of the rate. As a hint, we kind of figure out that this will be the expectation and this will be the variance, just because when you get the expectation here, if you get the expectation here, just because the expectation of this part is 0, we're just gonna live with the deterministic terms. And when you get the variance here, when we try to solve for the variance here, the variance of the deterministic terms will be 0. I'm just gonna live with the variance of this. And for this, you have to use the Ito isometry, because it will be the variance of the Brownian motion term. So this is what we're gonna do now. This will be very simple. It's just applying the expectation on the deterministic terms, and you just simply leave it like that. The explanation is just that the expectation of the summation of independent Brownian motions is 0. Now for the variance of this, just remember that variance of k of any deterministic term is 0. Variance of 5 is 0. Variance of a number is 0. So just gonna leave with the variance of the stochastic part. And we have some terms in T and a Brownian motion. So the variance of a deterministic, when you have a deterministic function of time on a Brownian motion, this is just constant. The variance of this you can use, because you have a deterministic function of time and you have a Brownian motion, you can use the Ito isometry, and this under these conditions, Ito isometry. So to understand the Ito isometry, we just need to remember that the variance can be decomposed into expectation terms, and remember that this term here was 0 because we had the summation of the Brownian motions. So actually, to calculate the variance, we just need to calculate the expectations of the term squares. So this is when the Ito isometry comes into the picture. Usually you see it starting with 0, the Ito isometry. It can also be proof that it holds when you start from any other position. So say you have this is what you want to calculate, the expectation of this under your measure, And sorry for that. So the eta isometry help us to deal with the integral of Brownian motion that usually we don't know how to calculate. It's not defined integrals of Brownian motion. So just get the part xt dt. This is an important term of the eta isometry. It just tells us just get what you had, square it, get the deterministic part, square it, and you'll have the integral of deterministic term. This is just also remember that dw is dt. So this is how the eta isometry can be very quickly explained. So we're gonna take this part, we're gonna square it, and this will be replaced by dt. This is how we're gonna apply the eta isometry here to solve for the variance. So remember, we wanted the variance of this term, and it will be just simply doing the expectation of what we had before squared. Just gonna square everything, and then on dt. So now we're gonna get rid of the terms that are not dependent on the integration variable. So before this, I'm just gonna put it out of the expectation part, the parts that do not depend on that are known already, that do not depend on the integration variables. And now we go. So we are left with just this term. So here, if you want, then you can change it. This will be simply then solving regular integral. So you'll have sky t. This goes out, e to kt. Remember, this goes out like this, and then to ks under, and the expectation of the deterministic part, we say that it was just a number. The expectation of the number is a number, and then we can simply cross out these terms. So the expectation, the variance, will be just what's left out. And this is also what you have, the textbook solutions for the Vasicek model. So RT in the end. So to simulate RT, you just need to simulate normals with this long expectation term here that is just a number. This is the rate today. This will be the term that controls the mean reversion, and then here the variance we just calculated. From here you can draw realizations of the rate. That's it for what is the expectation and the variance under of the rate under the Vasicek model. Now on what the remaining part of the video, I'm just gonna get the bond price under the Vasicek model. This will take us some time. So remember, the zero coupon bond price, this will be the zero coupon bond price under any, just by definition, under any model. So if your starting point is S and you have it for the price for some period t. The definition of any bond price is just get stochastic rate. Here it will be the Vasicek rate, and remember, whatever is known as of S is constant. And because RT was normal, so we have for any normal variable, just remember the expectation of X, if xt is normal, was just, we can write this as e to the expectation of, then x, if we continue with x, and then the variance of x. So this will allow us to have the bond price. This means to get the zero coupon bond price, we just need to know the expectation of this object and the variance of the same object. So what we need is the expectation now of the integral. It's not the same expectation that we had before, so we need to know the expectation of the integral and then also the variance of the integral. So we'll need to get RT and calculate the integral and then take the expectation and then take the variance. This is what takes some time because it's especially we'll have to deal with integration of Brownian motions, the stochastic integrals. So usually these models are solved with some tricks. Let's start off the expectation of the integral of RT. You can use many definitions of expectations. Just get the one that you feel more comfortable. This is one that you can use. What I would recommend is this one. Just expectation is, of course, linear operator. So you can decompose the expectation of RT in the expectation of some deterministic part as we did before, and then the expectation of the eta integral, that will be 0. So we just need to solve for this. So this approach is usually not recommendable. So we get now similar as before, but it's the expectation of the integral, and we're gonna go as well. From today it's gonna be S big T, and then here we'll have the RT going from some t, that now will be our final time, the starting point again. We're gonna use this representation of the mean reverting part. Don't forget here to change the limits, because these are the limits now that are changing, and all this is integrating by, that's why we change the limits, because we're integrating now in time. These are just we can apply integral as a linear operator, so we just need to do is just apply the integral in both parts, and then the expectation goes out, because the expectation of deterministic term is the deterministic term as well. Remember, expectation of 5 is 5. So take this out, that doesn't depend on dt, and you can then integrate what's left very quickly on dt. Just take the other constant out in Vasicek. Theta is constant, and here you just need to do algebra, that's it. And then this is on dt. Here as well you can linearly distribute the integral here. So remember, So yeah, I'm gonna remind you of a couple of tricks here. So here it just solved for the first one. So here you just go for the limits that you want, and here just you have the second limit. When you substitute, it will give you 0, right? And so here you will have this term, and now this term, just remember what we saw before. ST, this will be the same as, just put this here as the primitive, and this will give you, it's kind of t evaluated in t and t evaluated in s. You're gonna use this all the time in rates models. And so the first part is just gonna make like this, 1 over k e to the minus t minus s minus 1. Same trick. So now we're gonna see that the expectation of RTS is just right at the beginning, theta term, and then we get this out just for convenience. This sort of term will appear all the time in the Vasicek model and in other models that you will see. In the other rates models, you will encounter structures like this. Now, most of the books call this term, just for convenience, they call this B from S to T, because this term will appear all the time. So just name it with B. So now, to get the variance of the integral of the rate, we need the same thing. That will be the variance of the integral of the rate, actually, and I forgot all this. Starting from the information now of S. So just to get the variance, remember what we said before. If you have deterministic term, a term k or a term t, and then you have a stochastic term, then they are independent, uncorrelated, so just leave it with the variance. You can't live with the variance of the deterministic term. So that means that the only part that you have to calculate the variance will be the part dealing with the Brownian motion. So this will be, this integral here is just this integral here, and now we're gonna copy the part that has the Brownian motion term, that we left it with an integral just because you cannot do integrals of Brownian motions. Most cases, and there are some cases that you can apply some tricks, but it's just not defined. So this will be the integral in U. That's why we change it here, the limit, to avoid confusions on which is the deterministic term, and this is dt corresponding to this integral here, that is the integral that we need for the zero coupon bond. Just to avoid confusion, if now it's S and I have a bond maturing in t, say this is time, so my bond goes to from today, let's do it like this, let's do it in 0 is 1 time. Now we want to know the price of a bond that goes from here to here, just to get the rate. And then, so what we're saying is just get the short rate and the sum of the short rate that you are paid on every period, on every sub-interval here, and every dt. That will be the total interest that you get for of this bond. So this is this integral. Just say whatever you have, whatever you get paid, just sum it up, and that will be the total rate. And now we want to know the variance of this. and the variance of the process we had is just the variance of this term. So this is the STE term that we have, and this goes from the definition of a zero coupon bond. So I'm going to write down what we have in clear way. So we need to calculate the integral of an integral, and this will take us like 10 minutes because it's the integral, it's the iterated integral of a Brownian motion part, and then we had to take the variance of what's left off. So there will be a couple of tricks, and then I'm gonna try to use the less tricks possible, but you need to remember how to do iterated integrals, especially here that you had something that the integral is not actually defined. So the first thing we're gonna do is just try to get rid of one integral and deal with the exponential term. So for this, we're gonna do integration by parts, just because we have iterated integral over a stochastic term that, as I said, the integration is not defined. So you'll see how you get the integration by parts working. This will allow us to separate a little bit further what is deterministic and deal with the stochastic term. So first of all, just forget that we're doing the variance here and try to work with the inner terms. Let's split out a little bit what we can. So we can't actually split this term here because it only varies with the deterministic part. Then we're left off with something varying with the Brownian motion, and then something of the deterministic part that we're gonna write it. If you want, we can't write it like this. So just get out the dt term. So we're gonna now work with this dt term here, and we're gonna do this trick. So we're gonna write this term as just the derivative of an integral, just to have a product of two integrals then we can use in the integration by parts. Remember that in the integration by parts we need a product, and then one part, I mean, it's easier if you have a product and then one part will be derived and the other will be integrated. So by the fundamental theorem of calculus, derivative of an integral then is, as I said, is exactly the same this part here. So just gonna substitute this here, and then we're gonna have a product of two terms. The part that we're gonna deal with this later, and then I'm just gonna rewrite derivative of an integral from s to t. It's a different derivation variable. It's gonna have product, and because I've just substituted this part, this integral is always going to dt, and this is, now we're gonna apply parts integration, stochastic integration by parts in here. The stochastic integration by part works very similar to the integration by parts that we know. So if you have two terms that I'm gonna name A and dv, you have to identify which term you want it to be A and which one it's gonna be dv. So if you have this by the fundamental theorem of calculus again, you solving this is the same as solving it as these two terms here. So the trick is wisely name your terms A. The term that you name A is gonna be derived, and then the term that is V, it's gonna remain here, and then you'll have to integrate it. So there's gonna be a part that wouldn't have to be integrated, and then there's gonna be a part that has to be integrated. So probably for the Brownian motion, you wouldn't want to integrate it. So that will be the term that you'll leave it as it is. So we're gonna name this term to be the A, and then therefore the remaining part will be dv. So with this we can apply in stochastic integration by parts. So I'm gonna rewrite one more time what we had. So we had the sigma st, just to have it here, st. This is the part that we named it A, and now the remaining part will be dv. And we made this trick just to split into dv, this dt that corresponds to this integral here. So if you want to make it like this, and this dt here, that is from this dt here, that's it. So we have A, would say that it was this term here, k u t w u, and now what we need is dA over which variable? Over t, because that is the random variable. So we can have dA over dt. The differential of Brownian, the partial differential for Brownian motion, actually it kind of doesn't exist, so we're differentiating it. So we can actually have this. We're gonna actually have d st eku dwu dt, and then this will be just ekt dwt, right? It just because I'm making the differential with respect to the integration limits. Other way of seeing this is just our classical. In the normal calculus, what we will have is, if you have, say here you have b and here you have b, integration limits, then it's the same trick as we always had. Say for example you have something like this, so this f, when it integrates, becomes fb, and then the other limit is fa, and then apply derivative to both terms, this will be 0, and then apply derivative to this term, and this will be fb. So this is how to deal with derivative of the Brownian motion part. You can do this, just evaluate it on the integration limit that you have. Now we're gonna deal with the term dv, which we say was the same as we had dt, and now you have to integrate it dt from this dt here, and now by parts you just need to calculate the integral of this to make v, right? So the integral of this will be just st, what we had before, kv dv. Now I'm gonna write down one more time the integration by part formula to remember just what we were doing. So we had this, and now I need to put here A, and what we got as V is this one, and now then we'll need to evaluate it of the limits that we wanted, and then V one more time, dA, this part here. So we're gonna substitute and then evaluate from what we had before. So don't forget the sigma here, and then we go ST, the Brownian motion part that we had. This will be our V term, dV, and this will be evaluated on the original limits that we had. ST again, so we're doing this part, and then V again, and then dA. This goes with this, and this can go out because it's not on the integration limits. And also, so here we're gonna apply two tricks. This is gonna go out because it's not in the integration domain that we want, and also here we're gonna do this trick here because we have these integration limits here. This one will get substitute here, so we're gonna have everything. You'll see we're gonna have everything on ST integration limits, and this one we don't want to leave them on ST. We're gonna change this T to big T, doing the trick that you're gonna see now. So first thing is I'm gonna evaluate these two terms in my integration limits, which this means, one more time, sigma, that it just goes from the limits we had before. Now the integral will be evaluated in the new limits. This is how you apply the integration limit to integrals. ST. You see that we're getting everything in the same integration limits. ST everywhere. We get this out. KT, dW, T, and now we go. Split this into terms. So what we're doing here is just splitting the ST in these two terms, one on S, the other one going T, and then we say, well, but hold on, then because I went up to T, then I need to subtract the part that it's not on the original limits, like this. So it's basically having here that will be ST, and what we're saying is that this is like kind of going up to T, from S to T, and then just subtract the part that you need to leave off. That we're gonna deal with this later, but basically everything is going up to T, so this is what we wanted. And now we're gonna do just common factor everywhere. Gonna factorize this, gonna close this that goes with this one. I'm gonna factorize, and then there will be some terms that will cancel out. So we get this as common factor, and we have two terms with the stochastic integral just evaluated different regions, and these are all the stochastic terms, and just different evaluation variables, but these terms cancel out because it's the same variable. It just naming the evaluation term differently, but that doesn't change anything. So these guys will cancel out, and then we'll have left off this guy still is there, stochastic integral and deterministic integral. So we just need to then deal with this last part here, and we're gonna get something much simpler, that is just a deterministic part times a stochastic part that we can split it out like this. So now we can actually solve this part here. So we can then use the same tricks. E, K, T. This is going from T. Spit it out. This KT here. And now split this out here. When we evaluate it on T, and now this will go away with this, and this will be the difference on this. S T T W T. Here, making the algebra, and 1K. We're left off with these terms, TWT. So what we have here are just the internal parts. If we remember, what we wanted to do was to calculate this, right? RT, DT, FS. So what we have done up to here is just deal with this part. We also said that this was just the expectation of something something, that is this internal part. This was the isometry of something something square dt here. So what we have to do is effectively calculate this part here. Now, because it's the expectation of something on dt, this will be just the expectation of a deterministic variable. Remember, the expectation of k is k. And so that's why we can drop the expectation term out, because we're just dealing with something on dt when we do the isometry. So we're going to apply the isometry here, just like this. We're going to have the inside part square dt, as we saw before in the isometry. So here we go, everything square, and now that's the isometry, right? Everything square, and this term goes to dt. So we have first term, gonna write it down, square dt. This is the application of the isometry to calculate the variance. We can solve for this, and this is just a lot of algebra. ST1 dt s t e minus 2k t dt. Just everything stochastic, which makes it look easy. But it's just a lot of algebra. And we can't solve this. This will be the variance of the integral of the rate, Ts for the first term. Now, just gonna write the second term like this. And this is just the integral of the third term. What is this? Now, you can leave it like it is now, or you can just identify the BT terms out of here and here. So some books, what they do to ease the notation, they remember this, that we have called B any term that you have like this. We did this before. So we want this guy, this B, to appear, and we also want a B squared to appear, just to leave everything in terms of B and B squared. So if you square this B, you'll see that three terms appear. Remember, first one square, second one square, and then the difference of 2 times one times the other. So we want B square and B to appear. This term will contribute to B square, and this term will obviously contribute to B. This is just to change the notation. The solution is like this. This is just to change the notation. So you'll see the terms that in most textbooks appear, calling these terms B and B squared. So I'm going to show you how these terms appear, the step-by-step derivation. So here I'm just making this term appear for convenience. You will see it later. There are many ways to solve for this. There might even be easier ways and shorter ways. I think this is the way. So because I'm making this 2k appear, just need to then be careful with the other terms to still hold the equality. Now this 2k here then will help me out to make some of the other terms appear here. Now I'm gonna split this in two to make this 2 appear here, because I lost it now. So you'll see. It's 2k this term minus 1. I'm just doing this here now. This E is 2k minus S. 2 times what I had and now I'm going to factorize everything out. So there will be some terms that will cancel. First term appears as it is, it will stay as it is, this one. Second term, leave it as it is. I'm just gonna factor out factorize. So you'll see what gets. Just putting 2 inside. And now, yeah, I'm gonna factor out, distribute. Everything remains the same. 4. And you'll see here how some terms start cancel out with this one. This with this. So I'm just reading here what is left off, and now we're gonna take care of this term here and this term here that will cancel like this. So if you write just this, make this very simple thing, this 2, and then this guy will cancel with this 2 will cancel with this, and the 2 as well will simplify with this. And this is just a trick to get what you wanted on the format that you wanted, and to represent this equation in this way. It's a simplified way, but it doesn't change anything. It's just another way of writing the solution that you will see in most of textbooks. Write the solution like this. This is b from s to t, and this is actually k over 2 b squared s to t. So if you square this, you'll see that you will have this, but you need to add this term to make it equivalent. So what you have is actually that the variance of the integral of the rate. So remember, we need the variance of the integral from s to t of the rate starting from today, that we call it s. In most of the textbooks that you see the Vasicek model, you will see it written like this: minus bst minus k. See that I'm just changing the signs. Square. This is what we had derived. Now remember that the zero coupon bond, or actually we call it P, the price of a zero coupon bond from S to T was just the expectation, the exponential of the expectation of the rate plus 1/2 the variance of the rate s to t. So we got the expectation and we got the variance. Now if you just substitute this in here, you will get in a couple of lines the A that you see on textbooks. It's actually t e to the minus r s, and the b term s to t. Just substitute with the variance that we got and the expectation that we got. Thank you very much. As you can see, I have an awesome handwriting. I'm very proud of, and I'm sure no one else has this amazing handwriting of mine. So it is what it is. Thank you. Bye.